started. Oh. Okay, and share. Let me see. That should be the one. All right, how's that?
Yeah, it looks good.
We good? Fantastic. Sorry. Okay, yeah, thanks for coming, everybody. I haven't actually given one of these talks for a while. When she asked me, I realized it's about time for an update, because it occurred to me that a significant fraction of the group today was probably not here the last time I walked people through Enzian and explained things. So for that reason, I've sort of broken this talk into 3 parts. I will start by giving briefly, in an accelerated form, the usual spiel about why we did Enzian, why it's going to change the world, why you need a better machine for research. Then I'll go into a bit more detail about how things are looking today. You know, what are the recent developments for those who do remember the last talk, who do kind of know what Enzian's about but are not in the group, what's happened recently, what's new. And then I'll talk a bit about the ongoing research and where we're planning to go with it, and in particular how other people, especially within the group, can get involved. And that can be not necessarily by building part of it anymore. You can just, if you have an interesting application, something you'd like to try on it, then we actually have a cluster of the things now, which will at some point be going into the machine room and just be generally accessible. So without further ado, and feel free, if anybody has questions or comments, feel free to interrupt. We'll see how we go for time. Excuse me. But yes, feel free to just pop up and ask. Okay, whoop, where's the thing gone? Come on, there we go. All right, so what's Enzian? Why are we doing it? Well, as I said, this is the old story. The idea is we want to be able to do systems research. So for our group in particular, it was system software research. We came from an OS background. But the world has moved on since the platforms for which our current OSs and things were designed. We're getting a lot more custom hardware, excuse me, because it's becoming cheaper and easier to produce. And things like the end of Moore's law mean that branching out into other designs has become a necessity for really high performance stuff, in particular cloud data centers and AWS, among others, are already using things like FPGAs, and particularly Google's using things like the TPU and so on and so forth. The hardware that we actually have available as researchers and the hardware you work on has a really strong impact on the kind of decisions you make, or even the space of decisions that are open to you, the choices you are even able to make when designing something. And so we wanted to, put a stake in the ground and say, hey, look, we can step well outside of this commercial off-the-shelf kind of, Intel boxes running Linux with perhaps an InfiniBand card in them that we were seeing for a long time, right? And today I'm going to talk to you about how we actually went off and built this, what it looks like, and how you can use it. So motivation, whenever you see a talk about, this is a graph that I've shamelessly stolen from Gustavo at some point, right? Every one of these talks starts with this one, that we've reached the end of Moore's law, or Dennard scaling, or the power wall, or whatever it is, right? Something's growing really fast, but hardware has stopped. Right. And there's a couple of things you can substitute in here. The point of this graph is that there are a number of properties, there are a number of important metrics for hardware which have stored like this. So one, for example, very important one was the clock frequency. That happened a very long time ago. It's getting on 20 years ago now when we stalled on that. Then we hit the power wall. Now we're hitting the ends of scaling, where scaling to smaller transistors does not actually make it cheaper. It actually gets more expensive. Transistor counts, however, are still going up. We still build bigger things, but we don't get the free ride that we used to. And as a result, people have been branching out into different designs, and in many cases, revisiting designs that were proposed and in some cases already done to death 30, 40 years ago. But the landscape has changed, right? The particular details and the trade-offs between things are different now to what they were back then. So sometimes it makes sense to go back and evaluate the old ideas. Sometimes there are entire spaces, there are entire regions of the design space which have simply not been touched for various reasons. One, because maybe it's hard to go there technically, but a lot of the time, it's just that it was not commercially viable for somebody to build a platform out in that space. And for the longest time, even things like, say, FPGA accelerators, which it's gotten to the point where you barely even need to justify why you're playing with FPGA accelerators when you give your talk at Builder-B or SOSP or any other kind of top conference. You almost don't need to motivate. You say, yeah, FPGA offload, and people say, yeah, of course. But it's not that long ago where that was a crazy new idea, and why are you even considering this? You're insane. It's all going to fall in a heap, right? And so now we have a few of these point solutions, right? So you've got the AWS F1 instances with FPGAs. You've got other bits and bobs of custom hardware. You have Catapult, which actually went into Microsoft data centers with the FPGA. You have custom hardware like the Google's TPU and so on. So there's a few, a few instances of things outside the traditional paradigm, which is the available commercial hardware that we've got down the bottom there. But they only represent a few points in this space of possible designs. And they're the ones that made sense for a particular organization at a particular time, right? And we've gotten access to a number of these things, right? So we have a Catapult cluster that's still running down in the machine room. We worked on Heart for a while, so Heart wasn't actually commercialized. It's in the form that we saw it, but it was Intel's sort of first steps into the FPGA world. So we do get access to some of this stuff which is fantastic. But still, even when we do get that, we're still looking at a particular point where somebody else has already made the decisions. And what we want to do in research, and what our job is to explore the rest of that space, right? Is to find out where the other local maxima are that nobody else is looking at, because they, they need to make money in the next quarter. So we went off and built our own, right? Which is called Enzian. So this project started about 5 years ago now, at least the original ideas. I remember sitting at the lunch table with Mothi over in CAB at one point, and we started discussing it. And then I think the name we settled on the name a little while later. It was called Brisk for a while. You'll occasionally see references to that, but we settled on a proper name at the Systems Group retreat, actually, in Engelberg a few years ago. And being up in the mountains, we call it Enzian. And if you don't know, that's the little flower that grows right up high in the mountains, all over Europe. Okay, so from our side, this is I'm talking from what used to be sort of the Barrelfish NetOS group. Our real interest was in looking at system software, right? How do you manage, configure, secure these kind of new systems, right? And we had this great interest in it, and we got chatting about it with Gustavo at one point, and he was actually very interested in it from a database offload accelerator and other architectures, because this half of the group had been working on FPGAs for some time for offloading workloads, and this had the potential to be a useful platform for them. So what we ended up doing is sitting together and sort of brainstorming and coming up with something which kind of we thought and we hoped, and we still think it did, actually works as a platform for both of those, and incidentally for a lot of other people. There are a lot of other people outside the group who expressed a great deal of interest in being able to work on Enzian to try out all sorts of fancy new ideas they've got. What if we could have hardware that did blah, 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 blah. All right, we tried to get somebody to build it for us. We went to several companies who had form in this area. And the general response was, you're insane. No, we're not going to build that. There's no reason for us to build that. We're making money. And also, don't try. You'll kill yourself. So they were not wrong. We were insane. And we almost killed ourselves, but it worked. we did actually build one. So what we ended up with specifying is in the very simplest form, something like this, right? So our starting point, our sort of our non-negotiable requirement was that we can work with the native coherence protocol of the machine, right? We thought that there was a lot that was unexplored in the realm of very tight integration with the CPU. And in particular, the native protocol, right? Not some simplified or abstracted version of it, right? So yeah, something that runs over PCI Express. This was the core idea from which everything else built up, right? And this was so we were taking these decisions some years ago where there was some talk about protocols like Gen Z and particular CAPI, right? But there was nothing public, like the ideas of even what, things like CXL and C6, the other coherent accelerator protocols you'll hear about, excuse me, there was some noises about them, but there was absolutely no detail on it, right? So the context in which we were taking these decisions was one in which we had no confidence that these things would ever actually exist in real silicon. And to some extent that was borne out, right? So only a few of them have actually ended up in products, and it's not clear what the future of a lot of them is. CXL seems to be the only one, because it's backed by Intel, that is making it into hardware, but even then we're still not totally sure. Anyway, so the idea was to have something that runs over the native coherence interface of the CPU, get in as a lower level as possible, have something that looks realistic as a server CPU. So it has to be a realistically scaled server CPU we have to be able to get access to, and that means documentation as well for the native coherence protocol, and then put the biggest FPGA on it and as much RAM and network and whatever as you can get, right? To be maximally flexible. This is where we started from. And this is just reiterating what I said a little before, right? And that is that all the really interesting stuff from a sort of a systems perspective, from an offload design perspective, from a management perspective, from a performance perspective, all the really cool stuff is happening in custom hardware, right? So you think TPUs, think FPGA offloads, so on and so forth, right? What we need is a platform that lets us, as I said before, explore as much of that design space as possible, right? That doesn't limit us to what somebody else has decided is a good idea. Excuse me. And something that, as far as possible, can be reused and put together in different configurations to build bigger systems, to build different sorts of systems, to evaluate ideas against each other. So Enzian is intended to cover certainly everything that existing commercial systems can give us, plus a number of the use cases that we know. So we identified a few things. We said, okay, so HARP, Catapult, and a few others. We said, we must be able to do what those ones do, right? To be realistic. And in doing that, we will inevitably end up covering a larger region of the space. At least that's the idea, right? So we're not, for example, that dot that we don't cover might be perhaps a TPU, right? That's something that's much more heavily customized to a particular workload. So you couldn't really efficiently, simulate a TPU on Enzian, except fairly slowly on the FPGA. But a load of the other stuff, in particular, as you'll see, HARP, we absolutely can do. Enzian is a research computer. It is not built as a product, so it is not intended to be cost effective, right? It is not intended to run specific workloads well. It is intended for exploration. Now, as far as possible, you want to reuse, standard components so that you don't have to build absolutely everything from scratch. But the intention is that it is a platform for research. It is flexible. The goal is not to keep the unit price down, as you might do in a commercial thing. And so sometimes in the process of doing that, even for quite small savings in money, you see that engineers are quite aggressive at lopping off things that they decide we don't need, right? They'll decide, oh, no, you don't need that. We can save $1 a unit, right? And then when you come to do something interesting or funky, you find, oh, no, that doesn't work. They left it out, right? So the idea is that we would avoid ever doing that, right? Over-engineer it, put as much in as you can, then hopefully it's a realistic platform for a bit longer, and you're less likely to run into a case where something's missing that you would really like to play with. Excuse me. So as alluded to before, Enzian has grown into a bit of a monster, and the work that's gone into it, the fantastic and enormous amount of work that has gone into it is down to a large number of brilliant people who've worked enormously hard, right? And a significant fraction of the group has had some contact with Enzian, and a lot of previous members. And if I've left somebody off here, and I almost certainly have, I apologize. But what you're seeing here is the end result of an enormous amount of work by a large number of people. And I want to emphasize this, that this really was a big team effort. And of course, there's generous support from industry, in particular Xilinx, who donated FPGAs to us, and technical support, and Marvell, who were Cavium. So Cavium, who made the CPU we use, were bought by Marvell, and they provided us with an enormous amount of information about the chips, about the low-level protocol and support. They even handed us Verilog code for their implementation of it. Our implementation is not theirs, but that was a fantastic reference. So I need to thank them as well. So having said all that, there are now working machines, right? So this is a photo of the first one that we got working. You can see thermocouples coiled up on the top of the CPU and FPGA heatsinks there. This is the first one we brought up, and we needed to monitor it very carefully that we didn't melt a very expensive piece of unique hardware. Now there are actually 9 of these working. They're in a spare office at SDF at the moment. They're accessible over the network. In principle, they're available as of now for anybody to play with and try things out on. Talk to us, and you can get access if you'd like to. But this is what we ended up with in terms of specific hardware, right? So on the CPU side, you've got 2 40 gig Ethernet interfaces. These are directly, the Ethernet controllers there are directly on the coherent fabric inside the CPU. They're not over PCIe. And the network controller on the CPU there has an integrated match action switch. Right, so this is programmable like a P4 style programmable switch engine in it, which is really cool. And at some point, somebody should play with that. You get from the FPGA, you've got these 4 QSFP cages on the bottom, well, the middle left, I guess, over there, which will operate as 400 gigabit Ethernet interfaces. But you can also break them out because they're just running as the FPGA. You can break it out using different protocols, right? So you can, for example, run custom high-speed protocols. And if you run these individually, they'll actually run at about 32 gigabits a second per link. So each one of those connectors will give you about 128 gigabits, or 500, half a terabit of bandwidth on those connectors there. We're in the process of networking these up such that in the first cluster we build, I'll come back to that again later, the first proper cluster we build will have both of the 40 gig Ethernets and 2 of the 100 gig Ethernets wired into a full bisection bandwidth network for building up more complicated topologies or load generation, or working with RDMA offload, for example, all sorts of remote memory, near data processing, whatever it is, right? You should have an enormous amount of flexibility there. And then there's 2 left to play with, build point-to-point, topologies, build hypercubes, build folded cross networks, builds cliques, whatever it is you want to do. Okay, so there's a whole load of other stuff there. Most interesting, you have an enormous amount of DRAM. There are 8 DRAM channels, DDR4. The FPGA can take up to a terabyte, although the DIMMs you need to do that are excitingly expensive. They're about $4,000 a pop. More realistically, you can get a couple 100 gigabytes. You can easily get this thing to, say, 300 to 500 gigabytes for not too much money. And the machines we have, the 9 machines upstairs, have varying configurations of DRAM, but all in that range. So you have an enormous amount of DRAM bandwidth and also an enormous amount of capacity. And there's PCIe slots for future ideas. We're not actually using those as yet, but they're there because we had extra lanes available to do it. And again, if anybody has questions or anything you'd like to ask or comments, then feel free to put your hand up and interrupt at any point.
So David, I think there's a question in the chat.
Sorry, I'd not seeing the. Why am I not seeing the chat? It disappeared when it closed the chat when I started sharing. I see. From Shazan, is NVMe a better version of SATA? Yes, roughly. So what NVMe is at the physical layer is PCIe. So it is a PCIe, so it's a 4-lane PCIe link directly to the storage device. And it has a slightly different, well, fairly different command set to SATA, right, which is optimized for the fact that you've now got a very high bandwidth, low latency connection to it. So it's a different interface which goes directly over PCIe. You have dramatically higher bandwidth and lower latency to the things there. Yeah, exactly. And also there's all sorts of command set extensions for it for, byte addressable and blah, 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 blah. And there are 3 of those on the CPU, 1 on the FPGA, and the machines we have built have a back plane where you can put NVMe devices in, and we have some. We actually put NVMe in because Gustavo asked for it in the first instance, I recall. Because particularly because database folks are excited about faster storage. Okay, so here are the speeds and feeds. I won't go through all the numbers here. I'll put the slides up afterwards if you want to read them. You get an enormous amount of memory on both sides. We've got the fastest FPGA you can get. It's also very big. It's no longer the biggest they sell, but it's huge. Excuse me. Everything is as big as we could make. Oh, and in particular, for those of you who do OS and software development, we did all the little things that tend to be left out. So every UART on the CPU is brought out over USB. You have JTAG access to everything. Everything is accessible. All the little fiddly little bits that get coughed. This is the sort of thing where, where I was saying before that they'll save 50 cents by leaving off a UART pin out. Which, okay, fine for them, but as soon as you're trying to do low-level development, something's not working deep in your firmware, you can't do printf debugging. Well, on Enzian you can, because we connected everything. So the challenges we faced in actually doing this were significant. So as I said, we initially went to people who had built this sort of hardware in industry, and the general response is, yeah, cool idea, but you're insane. And yeah, as I said, they were right. Budget, obviously a concern. I mean, at ETH, we are fortunate enough to be comparatively well funded, but this is nevertheless an expensive exercise. Excuse me. The design and manufacturing costs up to this point are somewhere on the order of £500,000 francs, for reference, and this is then salaries for people are on top of that. So doable, but not cheap. But now that we've done that, the costs are amortized. Making additional boards, either for us or for other people who want them, is significantly cheaper. The unit cost for the boards, if you exclude the big old FPGA on it, which we had donated from Xilinx, and they have indicated that donations may be available to other people who need them and are in research and so on, is somewhere on the order of $10,000. And of course, this is a very rubbery figure, and this would depend on how many people wanted them. With a lot of this hardware construction stuff, there's a large setup cost, but the per unit cost, for example, for making PCBs is compared to the setup cost almost nothing. So it gets amortized out very quickly. Anyway, it's enormous board, 18 layers, signals up to 10 gigahertz. In fact, a bit more. You need to go to about 15 gigahertz for doing the 25 gigabit serial lanes needed for 100 gigabit Ethernet. Implementing the cache coherence protocol, that was a big job. I'm going to come back to that in a moment. Nobody's actually ever done this outside of, for example, I mean, obviously Intel or AMD or IBM will do it for their own chips, but actually interfacing to the native coherent interface of somebody else's chip is something which, as far as we know, nobody has ever attempted before. So it was a big unknown, but turned out protocol was pretty well designed. And we had some really brilliant, and still have some really brilliant postdocs and PhD students working on it, who were able to get it working for us, which was fantastic. We had never done any of this before, and then COVID hit, which was a bit of a bummer for everybody. So the last parts of the ring up process were done in lockdown. Why is this not? No, it is. Fantastic. All right, so as I said, probably the biggest single technical challenge was the coherent interconnect between the FPGA and the CPU. So a lot of the hardware design we did outsource. Like, we had to end up doing a lot of work on that ourselves, but at the end of the day, we were able to pay others to do it for us. ECI is, as I said, the core idea of the thing was that you would have the native inter-socket coherence protocol of the CPU, right, at the lowest possible level. ECI is our protocol which interoperates with the native protocol of the CPU, which is called CCPI from Cavium. Excuse me, I will come back to this again. An enormous amount of the work on this was done by Abhishek, who I'd like to credit explicitly here. I think he's not in the call today because he needs to be teaching. But, oh no, he is there. Oh, hello. No, I can't, like, I can see that you guys are in the room there, but I can't see who is there. Yeah, okay. Hello, Abhishek. Well done for getting ECI. Excuse me. So what exactly is ECI? Well, as I said, it's the native coherence protocol between the sockets, which means that it is symmetric and all the nodes are first class. What does that mean? So I'm going to contrast this with CXL, and the information on CXL we have is still preliminary, but based on there was a CXL talk a few weeks ago, and the documentation that's now available, as far as we can tell, CXL, this is one of the obvious things that people point out. Well, why don't you choose CXL? Well, CXL is an asymmetric protocol. It's very much oriented around the idea that the FPGA is something that is attached to a CPU, and the CPU is the core. In particular, as far as we can tell, a lot of the infrastructure, a lot of the hardware infrastructure, in particular the directory controller, that's the little DC block in there, is actually implemented on the CPU. What this means is that coherent accesses from the FPGA to its own DRAM on CXL need to query the CPU to see if there are cached values that it should use instead. Right? Excuse me. Now, this is a bit funny because this is exactly what a coherence protocol is supposed to avoid. Right? You're supposed to be able to check locally, or particularly when once you've got a directory, you should be able to check locally and figure out if it's possible that anybody else has a copy of this line that I should check. And on ECI, which is the left diagram there, this is exactly the case. Both sides have a directory controller. They're both first class members of the protocol. So they just check their own directory controller, which is kept up to date by synchronization messages at certain points, but does not force a round trip on every DRAM read. So this is an example of what ECI being implemented as it is on the native intersocket protocol gives you that something like CXL does not. Now, the coherent block in, say, an Intel Heart machine, which was an Intel CPU with what is now Intel FPGA, Altera FPGA, they had an implementation of QPI for you on there, of the coherent interconnect on there, which presumably could have done all of this, but didn't actually expose it to you. The interface you got was very, very limited to a particular use case. And so compared to something like that, we are giving you the flexibility to access it at a much, much deeper level. Again, I'll come back to that again in a moment. I have some examples of that. So that's what ECI is, when we built it. We also ended up having to build an enormous amount of tooling. So some of it's software, which it's kind of hard to take cool pictures of, unfortunately. But a lot of it was cool hardware that looks really good on slides. So on the left there, you see a prototype we built of the entire power tree of Enzian. So there are some dummy loads in there made from big resistors on heat sinks and regulators, so that you could fire up and down the different power rails, check how the regulators worked, build up your power sequences for turning the whole thing on. Because I mean, each of the chips on this thing, the big chips, can pull up to about 200 watts a pop. Right? They're pulling like well over 100 amps at just under a volt. So there's some serious amounts of energy moving around this thing. It's quite possible to set something on fire, right? With the amount of energy involved. So we built this thing, and this was how all the original firmware for controlling it was developed. In the top center there, you see the infrastructure we built for tracing the coherent link. So it's actually high-speed serial transceivers. So just like you would use in PCIe or modern Ethernet flavors, it's these high-speed serial transceivers, gigabit serial transceivers. And the nice thing about that is you can break it out to coaxial connectors. And we installed some T's, some taps there, and sent all the signals going both ways off to another FPGA, where we recorded them all. So we had these really high fidelity traces of 2-socket ThunderX systems, that's the chip we're using, where we could get every single interaction between the two of them. And then we built up a whole lot of software. Of course, I don't have pictures of the software for decoding these traces and building models. And we have had to generate, sort of a generation of masters and students, PhD students working on understanding this protocol, modeling it, formally modeling it, model checking, building simulators and whatnot. The top right there is custom hardware we did ourselves in order to interface to the development boards that we were gifted by Cavium. And so then we actually ended up building some test rigs. I'll come back to the testing stuff that you see at the bottom there, but we had to build a whole lot of our own hardware to do this. Having done that, we end up with a fully open source hardware design. So it took a while and a bit of negotiation, but we actually have all of the sources for the design. And you can actually open this thing up. You can zoom around the board, you can change component values, you can move things around, and then you could, if you wanted to, send your modified Enzian V3, 4, 5, 6 off to a fab house and get it built. And we will be publishing all of this, all of the sources needed to build your own Enzian. And this is the first time something on this scale has ever been published open source. We will be submitting this as an sort of appendix to the ASPLOS paper that was mentioned earlier. So anybody else who wants to understand how a thing like this is made or whatever, it will all be accessible to them. At the moment, it's all in proprietary formats from the tools, the vendor CAD tools, which is a pain. We intend to also convert it as far as possible into open formats. The extent to which that will actually work is still to be determined, but that's what we'd like to do. Okay, so brief timeline. Back in 2017, we had an Enzian V1. This was an FPGA board connected to a development board for the processor with a bit of custom hardware in the middle, and Mothy's very stylish science shoes at the bottom there that he took a photo of. Version 2, we built 2 of those, put them in little rack things. These still live, I can see them in front of me in H319. This was the first kind of real Enzian. And this was most of the software and firmware development work was done on this, the bringing up of ECI and whatnot. And yes, so they're still live today and are used occasionally, although with the delivery of the final boards, they're mostly obsolete at this point. As of 2019, we had the full design, though not yet the hardware. This was the first render we got back from our design contractors of the board. And this is what we started working on now. And here you've got the full block diagram of the thing. And I would like to highlight in the middle there, as of a few days ago. So the theoretical bandwidth of ECI, so this is just the raw bit rate across the wires, is 30 gigabytes a second. As of a few days ago, we have achieved 22 gigabytes a second. That's good put. That's actual message coming back from the FPGA. So we're getting close to the actual theoretical throughput of the thing. B or B from, yeah, that would, sorry, you're quite right. That should be big B. That's bytes. Yes, it should, yes, that should be a big B. It's bytes in both cases, 22 gigabytes a second. So we've cracked 2/3 of the theoretical. So there's not much more there. Once you take into account protocol overheads and things. And again, this was something that Abhishek achieved recently with an updated block packing, which was really, really cool. In 2020, we got the first actual final hardware. This came while we were in lockdown. The first board was actually delivered to my apartment while we were working from home, unboxed it there. And if we had to negotiate a little later to actually get it physically into ETH. So we were some of the first people to actually come back into CAB just to set the board up so that we could start playing with it. And I said to bring up here, this was when we first powered the thing on. You can see that it's all powered up through lab power supplies with current limiting and an oscilloscope attached to it. And that thing down the front is a debugger and a little temperature. That's the black box is a thermocouple temperature monitor. We very, very carefully and slowly brought this thing up. We had some rather exciting moments in doing so. And that was done in the summer of last year. To our great joy, it worked. And we had one working Enzian V3. It existed. Then, of course, we moved over here to SDF. We packed everything into the truck and drove it down. I drove that truck down the hill myself. we all casted the very precious trolley there into that. That's out the back of CAB. Most of you will probably recognize that. And as of today, we have an interim cluster. This is sitting in one of the as yet unused offices on the J floor of SDF. There are 9 Enzians plugged together in there on a 100 gigabit switch. Those are on the network. So this is not, of course, the long-term plan. These will be going into a rack with a more extensive networking and proper calling and everything. But this gives us the opportunity to actually work out how these things should be integrated into a cluster. It gives a platform to work on. And if anybody's interested, then they're more than welcome to come and ask, and I can show you around up there. So as of today, we have people working on artifacts, an artifact submission for the ASPOS paper, and all that work is happening on the live cluster, which is sitting on J floor of SDF. So that was the history. Things we learned in doing that. Debugging this interconnect was an enormous amount of work. Probably the biggest single job was implementing and debugging ECI, and it's still not done, right? This picture you've got here is just a zoomed in one of the one I showed you before, where we tapped the lines between the two Thunder X's and literally dumped everything they said to each other. That was enormously useful. No matter how well designed the protocol is, and it is actually a very nice protocol, these things are never really intended to talk to anything but themselves, right? So there isn't really a specification of the protocol for these things. The specification is, generally speaking, the implementation. They're only intended to talk to themselves. So occasionally you run into cases where it just assumes that the other side behaves like it does, even though that's never actually specified anywhere. That was all fun, but this is all pretty doable once you have the raw traces. You put a bit of brainwork into it and you figure this stuff out. And the students, and a lot of this was actually done by master students doing theses, figured a lot of this stuff out. Not only were we responsible for the protocol layer, we were responsible for the actual physical electrical layer. We did the electrical testing for our, so as I said, we contracted out the design to a company in Germany called Dreamchip, who've since been acquired and are off doing other things. But as part of the negotiation of that contract and to get it done at a reasonable price, we agreed that we would actually do the electrical testing the high speed, of the really high speed signals. And this was a very fun project. This happened towards the end of 2019, beginning of 2020, where I and Michael and a few others, we went off and actually built some real things out of metal. That thing you see on the left is a big XY table, which lets you move these little probes. So the thing on, or what you're seeing on the right there is a very zoomed in view of the actual probes on the 25 gigabit and the 10 gigabit signal pads, right? And those hook up to a vector network analyzer that we borrowed over at ETH that let us get, you know, detailed characterizations of the things of the behavior of the interconnect in the microwave frequency range. And we were able to send those back over to the design team, and they could, yeah, they were able to say, yes, okay, that matched our predictions. So yes, we're good to go. Unfortunately, when we're right in the middle of doing this testing, is when the first lockdown hit for COVID. And so I had this idea that we'd get a full characterization of all of the pairs, and then we'd have this really cool data set to release where you can say, okay, here's our open source design, here's the simulation results, here's the actual measured results, right? And for somebody who's working in the center, that might be a cool thing to have. But yes, we got interrupted by COVID. So this is still on the back burner of something that if somebody would like to do this, then talk to me. If this stuff looks cool, somebody to actually finish this characterization would be awesome. We have all the hardware sitting downstairs. Okay, we learned an enormous number of things. Hardware is much more complicated than it looks. You might think a regulator is just something that takes in a high voltage, pops out a low voltage. Well, it isn't. These things are incredibly complicated. Some of these things have hundreds of configuration registers. The amount of work you need to put in to actually configure and manage the power delivery and fans and thermal control and everything network on these machines is just fantastic. And this was something which we kind of understood in theory when we started, but it really got driven home to us exactly how much of a big problem this is. And consequently, a significant amount of research that we've done since has, sorry, clicked on the wrong thing, has been driven by these observations. So there are now additional research projects, basically just looking at the baseboard management controller and the power delivery networks, automatic synthesis of power up sequences, so using SMT solvers and whatnot. So we've had a number of students, again, a number of brilliant students working on this. And there was a paper on that just earlier in the year. So this has actually led to an entire extra line of research in the group on how to do the low-level management stuff of this in a reliable, hopefully verifiable, well-documented, declarative way. And this is, so if you see our students talking about BMCs and declarative power management and sequence generation, this has all come out of the complexity we discovered in building this board and working out how to bring it up. Right. And we have all this tooling around now, all these machines for them to test their stuff on. Oh, I've lost the thing again. Okay. Hardware turns out to be really, really complicated. High frequency stuff is hard, although not as hard as we thought. Actually, they're doing stuff at 10 gigahertz, which sounds really scary, and it was certainly scary to us because we didn't know what we were doing, turned out to be one of the less hard things. Actually configuring the power regulators correctly, much more work than getting the high frequency stuff to work properly. That stuff basically just works. Has been our so it is what we've discovered so far. So we've had these cases where, we've taken these 10 gigabit links and we've like plugged them through hand soldered adapters, several chains long, and they still just work, right? This stuff is pretty robust. That was something that we were not expecting. It was cool, but this is a lovely photo of Michael sitting on the office floor over in CAB assembling some of our heavy metal testing hardware. This was right in the thick of the construction. Oh, where are we? Oh yes, and this was the bring up. This was the chat log that Mothi captured. I didn't realize he was doing this, of Adam and I talking back and forth if you can't see it properly, I'll put the slides up and you can have a read. But this is when this is the first time we ever turned the CPU on. And of course, we immediately blew the circuit breaker or flipped the current limit on the thing. Turned out it was drawing almost 200 watts. We later discovered that this is just a transient thing. It does that. It takes its enormous transient power before it settles down again. So actually it's fine, right? But it was a very scary moment that it looked like that we'd killed it. But that was fun. And this was all during lockdown. I was the only one in the office and everybody else was remote, hence why it was done over Mattermost. Okay, so I've given you a bit of a summary of why we built Enzian, what it was for, what we ended up building, some of the stories about what happened while we were building it, what was hard, what was easy. So some of the final stuff in here, I'll go over a bit quicker because we're getting sort of close to time here. I wanted to make sure that when we put these slides up, that if somebody wants to come back and have a look, you know, I'd sort of credited everything and we'd seen, you know, information. So I won't necessarily go through all of it in intense detail, but the slides will all go up so you can have a look through. But in terms of ongoing work, things we're doing now, well, as I said, we took these very detailed traces of ECI of the existing protocol. So what we traced was CCPI, that was KVM's original implementation. And now we have this entire family of models, formal models, simulators and whatnot built on top of it. Work on that is ongoing. The models derived in that are used in the current implementation of ECI, right? So some of the directory controller that Abhishek wrote, some of the state tables and that are generated automatically from the specifications we reverse engineered from the protocol. As I said, this is the stuff we captured off the wire. As mentioned, we have this entire new direction in research, which is managing these enormously complex physical systems that are motherboards. And that you've got this little bit in the middle there, right? You've got this little thing called the BMC, the Baseboard Management Controller, which is responsible for all of it. And generally speaking, the software quality on these things is terrible, right? So on the right here, what you've got is, you're not supposed to be able to read it. The point is just to see that that's complex. That's the power tree for Enzian. That's all the different regulators. That's not all of it. That's the simplified version. And this is what you need to control. You make sure these things come on in the right order. You never go over power. You never go over voltage or over current on anything. A lot of this stuff is managed from a BMC, and this is true in every machine you've got now. Every machine has one of these now. And the state of the art we discovered is largely shell scripts running on top of Linux, right? That runs all this stuff. This is what this real-time, you know, supercritical and also security critical, the BMC can completely take over the machine. It has access at the very lowest layer to everything, right? And these things are generally on the network. You can SSH to them. Right? So there's this massive bubbling away problem at the bottom here, right? Which we're not the first to discover it, but it's become very clear to us. And so we have a whole line of research in trying to fix this. This is what the one on Enzian looks like. It's got a little FPGA because we couldn't help ourselves put a bit more complexity in there. But yeah, the software quality and the sort of the quality of the design down there is actually quite low compared to how important it is. Literally every server on the planet is running on top of one of these. Right? And if this is vulnerable, they are all vulnerable. If it sets voltages wrong, your CPU catches fire. The state of the art is off-the-shelf software. Right? OpenEMC BMC is cool. I'm not specifically knocking it, but it's not high assurance stuff, right? We'd like to put it on a bit of a firmer foundation. So we have a project going on now to actually put it on something like SEL4, because the BMC actually runs ARM. ARM is SEL4, this is the verified microkernel, runs on ARM. And the idea is that you virtualize something like OpenBMC, and then you pull off the highly trusted components, the hardware, you know, the voltage monitoring, control, security critical stuff into separate components and verify those separately. So this is the direction that Daniel is taking in his PhD work. So he's looking at how you build a BMC for this sort of thing. And more specifically, Ben, who has just joined us as a PhD student and is, I assume, in that room up there somewhere, but I can't see him. There he is, he's waving. Hello. He, for his master's thesis, actually did verified a simple version of a power management controller for Enzian on top of SEL4. So the idea being that you take this little component, right? You pop it outside OpenEMC, you verify that it does its part correctly. And he did actually manage to prove correctness for it. And we're now looking at how to extend that work, in particular, moving on to ARMv8 onto more modern hardware, so we can do better virtualization. And we're in talks with the SEL4 folks about how to go on with this. Yeah, it's basically everything I just said. And this comes under the umbrella now, kind of the Sockeye project, which is an additional project in the group, which I'm not going to talk about now, which is about the formal specification and declarative specification of hardware, tackling hardware complexity. We have some sort of synergies there, to use management speak. ECI itself, as I said, it was quite a nicely designed protocol, and there's still an enormous amount of work going into implementing and verifying it. It's layered. I won't go into all the details of it, but it's a fairly nicely layered protocol. You've got the physical high-speed serial down there, and it's broken up quite nicely. And at the top level, what you get are effectively flits. You get little messages saying, please evict this cache line, please upgrade this line for me. These pop out at the top, and this is the layer that's implemented and now runs at 22 gigabytes a second. So this layer is pretty solid now, and we're looking at how to build stuff on top of it. Right. So in order to know what you should build on top of it, there is no single answer, right? The first thing to note is that there is no single way to use something like ECI. The whole point of it is to be flexible. Here are 3 representative use cases that we're using to drive our thinking, right? The first is on the left, where it's more like a traditional, say, PCIe attached to accelerator, which has its own RAM, excuse me, and is acting as a device, right? Then you've got an FPGA acting as a peer, where it's also first class in the protocol. Or on the right, you're acting as something like a smart memory controller, where you're doing it back to data reduction or some near data processing. Right? All of these different ways of using a coherent interconnect place different demands on that interconnect. And so it makes sense to think about having different implementations, right, or different variants of that interconnect between those. And that's the future of the ongoing work on ECI. Is how to optimize for these different cases. What do they need? What do they not need? And how should this inform our thinking about coherence protocols in general and the interconnects for accelerators in particular? Excuse me. Oh, here's the performance graph. So again, I'll just put this up. But yes, we're getting up to 22 gigabytes a second over ECI, and the latency is like under 200 nanoseconds, which is that's round trip, by the way. So this is even better than the last figure. I've been quoting a figure of about 400 to people, so we're now down below 200. So this in terms of performance, this blows anything else, even on the commercial market, out of the water. Right? Nobody else is close to this. So we've got something that nobody else has here, which is really, really cool. Needless to say. So yeah, I'll go quickly through the last parts. So the initial crack at a directional controller, this is the thing that tracks what state all the cache lines are in, we generated from Abhishek, generated from the models, the formal models we developed through reverse engineering and verification. Worked perfectly well, but wasn't really fast enough for us. So the work now is on making a scalable and particular, not just scalable, but also customizable implementation. So you can say, well, I need coherence for this thing and this sort of coherence. This is doing read-only workloads, or this needs to potentially evict things on the other side. And what you do is you take the model for all of ECI, then you subset it. So all of ECI itself is the native protocol of the processor, the ThunderX processor, is Merzi. we implement a subset, a messy subset of that, right? It just simplifies it down a little bit with some optimizations, but you can go even further. If you discover that what you need actually requires less than this, and this is something that we managed to do, it's in a paper that's under submission now. If you discover that you're not actually using the full power of the coherence protocol, then you can actually take a subset of the states and the transitions, and then you would generate a customized directory controller for just the subset that you're actually using, right? And this saves you an awful lot of resources and gets you better performance. But this is ongoing work, right? This is stuff to which I don't have all the answers as yet, right? I already mentioned high-speed tracing of ECI, but we did this both offline. Now it works online. So we've had a series of students. One of them is Tom, who is, I think, in the call somewhere, was involved in this work. So I don't know. He's now a PhD student here as well, with Anna, and he was involved with this. This was compiling down from LTL specifications of properties that you'd like to check in real time on this extremely fast protocol. Compile these down into automata, which are run on the FPGA. FPGAs are very, very good at running automata like this. And then you can run them in real time. You can check things you'd like to check or count things you'd like to count on the protocol. For example, and this is from a follow-up work, another master student who came afterwards was able to, for example, tell apart different types of misses in the last level cache, right? So you run a binary search and you can see that the pattern of conflict versus compulsory misses is what you would predict based on the access pattern. This is from his thesis. That's also ongoing. How to use this. This is now a tool for debugging your applications on top of something with ECI. So applications quickly. So obviously in this group, we also have an OS for FPGA accelerators, Coyote, which Dario wrote. I think Dario's here somewhere. This runs, so Coyote has been ported to Enzian, runs on Enzian. So anything that runs on Coyote now in principle runs on Enzian. We're working on better integration. Currently, the build system on Enzian is a bit of a mess, but this is getting better. Stream processing. So this is Anastasia, who is working on timely data flow offloading to FPGAs, and discovered that a big bottleneck is the need to do batching back and forth to a contemporary, a standard accelerator will tend to do batching back and forth. So with OpenCL, you'll copy large amounts of data back and forth between computation rounds. She's hoping to be able to accelerate this fairly dramatically by doing fine-grained sharing, utilizing the Coherence protocol. And the fact that we have our own platform, we designed and built it ourselves, means that we actually had the opportunity to make sure it was heavily instrumented. In particular, all of the regulators, all of the power lines, so all of the voltage levels, all of the current levels, temperatures, everything else can be monitored as you run. So you can do all sorts of really cool stuff with this. And so we had a master student who worked on this with, and that was under Michael, who was also in the room up there, I think. So for example, here is live measurements of the power utilization of the system under various workloads. So you can see that as you ramp up the power in the FPGA, you can see the power in the DRAM up the top there, stacked on top. Zooming in, right? So this is sort of broad strokes. You can get very detailed power measurements of different parts of the system. If you go even finer, right, you can actually see some very, very cool stuff, right? And this is out of Christina's thesis. That you can actually spot the correlations between, in the first and the top left there, you can see a very clear correlation between the IPC, right, instructions per cycle on the CPU, and the power draw of the CPU. And part of what you can see there is the effect of the high static power distribution of this particular CPU. And on the right there, even more dramatically, you can see the very close correlation between the last level cache miss rate and the power used by the DRAM. Right, so this is demonstrating that you've now got a tool for very fine-grained insight into performance on your platform. So this is another application of the thing. Okay, so I apologize for going a little over time. we had so much to cover. So what's happening now? Well, we have an enormous amount of ideas, things that we'd like to try. So this is talking for the Enzian team. We have some people, we have some external folks who are pretty keen. In fact, we already have one group at Boston University who are working on something on top of Enzian. But this is me calling again for anybody in the systems group who has ideas or would like to play with this, then please come and talk to us. We're more than happy to help you try and get your ideas on Enzian. See if this can be useful to you in some way. I'll skip that part. Yeah, so that's where I'll leave it. This is a tool we have built. It's here. It's available to all of you. We are, happy for contributions, criticism, discussion. Jump in.
Thanks, David, for the very inspiring talk. Although we're a bit over time, I think people are generally very interested in this project. So we can keep the discussion on as long as, David, you're available.
Yeah, I'm available. So yeah, so sorry for going over, but yes, no, I'm available to stay for anybody who'd like to ask questions. I think Gislan has put his hand up.
So, thanks a lot. So it was a very good talk. It was very nice to get this update on Enzian. I'm going to ask a question that's going to sound scary, but it might be actually an interesting research direction. I'm also going to explain why I'm asking this question. Mm-hmm. It's about what Bell inequalities would look like for systems with a CPU versus systems with a CPU and FPGA. The reason I'm asking is that adding this new hardware, FPGA on top of a CPU, extends the limits, as you said at the beginning of your talk, where you are going. What are Bell inequalities in quantum physics? It's actually very simple to explain. There are experiments where you have random variables, so you have a joint probability, typically on 4 variables. So typically you have all the possible assignments that these probabilities can have. So you're in a hypercube of dimension 16, basically. And there is a simplex that is just the shape of the zone where these values are allowed to be for a classical computer, for a quantum computer. What a Bell inequality is, it's just an equation for one of the faces of the simplex. And so the reason I'm asking is I suspect that in the case of what you're doing, and you showed this graph with latency throughputs that might be some of the dimensions, what would this simplex look like for a CPU, for an FPGA? What are the theoretical limits? Could we quantify that in terms of simplex equations?
So that's an interesting question. The way I would have to, I think, mentally frame it, I would think in terms of sort of Pareto frontier, or, and that's actually a very interesting question. And I think it depends a lot on what you consider the constraints to be. One of the, so if you take it to be just like ASIC on the CPU side versus FPGA, then obviously the ASIC can beat it in any way. But once you've fixed a particular CPU, right, then what can you do with the fact that you can change the FPGA? And I think one of the really interesting places to look at that is in terms of power usage, because you get this sort of counterintuitive result with FPGAs, right? That FPGAs are actually, for any given computation, the FPGA implementation of it is dramatically less efficient than the CPU computation, right? Because it's working at a level of abstraction higher. But in practice, the FPGAs actually very often end up saving a lot of power because there's a lot of stuff the CPU is doing that's optimizing for a case that isn't actually happening. So I think, yes, there's an interesting question about the trade-offs and actually characterizing the trade-offs. When is it worth the offload? And what is the cost of the data movement, for example, across the interconnect versus doing something locally, is a very interesting thing to look at. Yes, I agree. I don't have a more detailed, a more precise answer there off the top of my head, but yes, it's an interesting question. Thank you.
I think it would be a long-term direction anyway. It's not the sort of thing you can do in 1 minute.
No.
But it makes a lot of sense. So power would be what?
Yeah, I think power is a very interesting thing to look at. And Michael is actually looking at power usage on, If there are any other questions, then I'm more than happy. So I don't want to keep anybody here if they have anything else to do, but I'm more than happy to stay and answer questions.
Yeah, so David, I have one question. So you talked about the ECI link.
Yes.
So I'm asking for some more specific use case of that, because
Yep.
there's no application that pop into my mind immediately that specifically require the coherence at that fine-grained level. Do you have more examples about?
Yes. So this is, yes, another thing that I didn't have time to go into, but we have enumerated a few in the recent papers that we've submitted. One example is, for example, would be a materialized view. So imagine that you have a very large data set, right? So large that it's actually got to sit on secondary storage, say over in NVMe or something, right? And then you have a very costly computation to generate a view on that data set, right? So it's the result of an expensive query, right? Now the cost of regenerating that data, regenerating the part of that query is very, very high, right? And you may want to use it in a complicated fashion, right? You may need to walk back and forth over it in a complicated way because maybe you're doing a matrix multiply on top of it or something, right? Something that has a defined locality, temporal and spatial locality behavior, right? And if it falls into the class of things where the last level cache of the CPU is well designed to handle it, right, that it handles that kind of temporal locality very well, then what you will find is that the caching system within the CPU transparently and automatically, with no extra effort on your part, caches the results of your very expensive query, right? And make sure that they are invalidated. So for example, some part of the data set down there changes. As long as if you can efficiently determine which parts of the materialized view depend on that part of the data set that was invalidated, then you can efficiently generate evictions, right? To make sure that the view always remains consistent. So that's an example of a workload where we see coherence being really useful. I mean, we came up with some toy examples of it in the paper just to show that it would work. But that's an example.
Yeah, that's a very good use case. Any other questions?
Feel free to come by and talk offline. You know, I don't mind.
Sure. I think many people have already involved in the project, so they
Yes.
already know
There
a
are
lot
plenty
of
of people
details.
already, yes.
Yes,
precisely.
So yeah, thanks David again for the very, very inspiring talk, and I'm looking forward to the updates of this project. And see you guys next week.
Bye.
Bye-bye.
Thank you. Thanks a lot. Bye, everyone.
Bye.